Hi class, welcome back. Today we're going to discuss 5.3 inverse functions. The objectives are to verify the one function, its inverse function of another function, determine whether a function has an inverse function, and find the derivative of an inverse function. So a lot of the topics, in fact, 3/4 of this lecture will be regarding to what we learned in college algebra. So it'll be a quick, brief review of inverse functions. So here we go. The function f of x equals x plus 3 from a domain function 1, 2, 3, 4 to b 4, 5, 6, 7. So if you notice, if you plug in 1, 1 plus 3 is 4. Plug in 2, 2 plus 3 is 5. 3 plug in plus 3 will be 6, and 4 plus 3 is 7. So this is what we call the domain of the function, and this is the range of the function. And we write it, we can write this relationship as f such that we have these order pairs, right? 1 really corresponds to 4, 2 corresponds to 5, 3 corresponds to 6, 4 corresponds to 7. In fact, we even give them a label. This is x, this is y, x, y, x, y, x, y. So in theory, what's happening is that we have this domain set of numbers, right? We have a set of numbers where the function f is mapping those numbers to a specific set of numbers on the range. So this is another set. But what's going to happen when we talk about inverse undoes what the function has done. So it's going to map back the number back to its original number. For example, in this problem, we had 1 being mapped to 4, right? So what the inverse is going to do is going to take, and so what happens here is this is f of 1 equals 4. So what's going to happen here is maybe I'll write it over here. So in the process, sort of like a portal, right? It took f of 1 and then map it to 4. Well, what's happening over here is taking 4 and mapping it back to 1. So what's doing is the inverse of 4 is being mapped back to 1, right? So what happens here is that this is your x value, this is your y value. But for the inverse function, this is sort of the x component and this is the y component, right? If you guys notice, it maps 4 to 1, it maps 5 to 2, it maps 6 to 3, it maps 7 to 4. So if you guys remember from algebra, we started talked about that, right? That the inverse function is sort of the reverse, the interchange. I'm going to write that word here. Is the interchange of the original relationship. So by interchanging the first and second coordinates of each order pair, you can form the inverse function of f. This function is denoted as f -1, right? And we don't call this f to the power of -1. So please be careful. We don't. This is not how we read this. We read this f inverse. And so it is a function from b to a. So this is your a, this is your b, right? So it's a function from b to a, right? And it's written in that form. Note the domain of f is equal to the range of f inverse, right? So the domain, so what happens here is that the domain of f becomes the range of f inverse, right? This is domain, this is the range for f. But for f inverse, this is the domain and this is the range. So domain of f is the range of f inverse, and vice versa. The range of f is the domain of f inverse. Now, one of the special properties of being inverse functions is that the composition between f and f inverse is going to give you the original value. So and it will satisfy both directions, right? So that means f of f inverse of x is going to equal x, and f inverse of f of x is going to equal x. So we must satisfy those two conditions in order for the inverse function to be true. And that's sort of what happens in the next definition, right? So we're gonna write this. Erase this. Okay. All right. So the definition states a function g is the inverse function of the function f whenever the following two are true. The first one, it says that f of g of x gives you back x. In a way, they undo each other, right? Give you back x. And then in this case, x is in the domain of g. X is in the domain of g, right? Because you can only, in theory, this x came from the domain of g, right? Initiated from there. And then this also needs to be true. That means when you reverse the composition operation of the two functions, you're still gonna get back x, right? In order for this to be inverse. So g of f of x will give you x. And in this case, x is in the domain of f. If you notice, x is in the domain of f. So the function g is denoted to be f inverse. And that's how we're gonna read it. So do not say this as f power -1. That's not the same thing. They're not. This is not a power. This is a notation. Let me write that out. This is not a power. Not a power. This is a notation. Notation. What I mean by notation is just a mark, right? It's just, we could have just written this as this, whatever, right? Anything, or we could have just written this like this, something like that, right? It's just a notation that somebody came up with and stated that that's going to be your f inverse notation. But I get it. It is confusing because it looks like a power, but it's not a power. All right. So here are some important observations about inverse functions. If g is the inverse of f, then f is also the inverse of g. That's sort of kind of like a logic argument. The domain of f inverse is equal to the range of f. We already mentioned that. But vice versa is also true. The range of f inverse is equal to the domain of f. A function need not have an inverse function, but it does. But if it does, the inverse function is unique. So what we're saying is, just because you're a function, it doesn't mean you have to have an inverse function, as we're gonna see in some cases. Now, if the function does have an inverse function, we're gonna say that function is unique, meaning that there's no function that has two different inverse functions. You can think of f inverse as undoing what has been done by f. For example, subtraction can be used to undo addition, and division can be used to undo multiplication. So, f of x is equal to x plus c, and f inverse is x minus c. It's undoing the addition of c. This is undoing the subtraction of c, right? Are inverse functions of each other. Just like f of x is equal to c over times x, the inverse function will be x over c, where c cannot be 0. These are inverse functions of each other. So let's verify the following function are inverse of each other. So we're given f of x and we're given g of x of this form. They want us to check whether these are inverse of each other. Now, to check that these are inverse of each other, we have to use the composition operation. What does that mean? We're going to try first f of g of x. So we're going to do that. What does that mean? Is that we're going to replace g for every x that we see in the function. So we're going to replace this g in here and in there. So I drew an outline of the function f, and then I plug in g. All right, you guys see that g right there? And then what I'm going to do is I'm going to go ahead and simplify it. Well, first of all, the cube root and the cube power are going to undo each other, followed by x plus 1 over 2 times 2. Well, these 2's were going to undo each other, and now we're left with x plus 1 minus 1, and we can see that plus 1 and minus 1 will do on each other, so we get back to x. Now, some of you might think, well, we're done. Well, not necessarily, because the rule of inverse states that both need to be true, both directions. Now, there might be cases where it will give you x for this order, but it won't give you x for that order, right? So you still have to check both of them. It's a must. So what we're going to do here is the reverse order. We're going to do g of f of x. So we're going to take f of x and we're going to plug it into g. So wherever we see an x, we're going to replace it with f of x. So replace that x with f of x. So that's what we did. We have the outline of g first. This would have been my x, and I replace it with f of x. Then what we're going to do is we're going to start simplifying. The minus 1 and the plus 1 will cancel each other out. Then we have the 2 and the 2 will cancel each other out. And then now we're left with x cubed to the cube root. And then these one do each other, giving you back x. So we can clearly see that these two are inverse of each other. So we can label g to be f inverse. Now, what is interesting for us, now that we have seen this, right, we're sort of done with this part of the problem, but what's interesting for us to make note is this picture. And we talked about this in college algebra, but I want to make sure I emphasize this again. This was the original function here, right? This is the sketch of the original function, and this is the inverse function, right? Did you guys see some pattern in this example? It seems like this inverse happens to be the image, the exact image of the original function in respect to this diagonal line. Meaning, if you have this diagonal line, this function is being mirrored on with respect to that line, and it is true. It is always true. In fact, that's one of the special conditions of being an inverse function, is that they're gonna mirror each other out in this diagonal, right? And is that surprising? No, actually, it's not. We should be able to think about this as remember that the inverse function is the reverse order of the order pairs. So, for example, this is what 0, -1. Well, what is this? -1, 0. So what about this point right here? This is sort of almost it's hard to tell what number is that, but if you're gonna notice, this problem is probably like what, negative let's say -0.7 comma -2. Well, what is this gonna be, this number right here? Well, this is gonna be -2 comma -0.7, right? So they're just mirroring each other. All right, moving on. Well, this is sort of an important theorem that we can utilize. This is known as the reflective property of an inverse function. The graph f contains the point AB if and only if the graph of f inverse contains the point BA. So we reverse the order, right? Interchange A and B. And that's sort of what we have here, right? This is another example where if you have your original function, the inverse function will be a mirror image of that using this diagonal line. Okay, moving on. In the next line, we're going to discuss the existence of an inverse function. So it's important for us to know when a function has an inverse, right? And so we're going to develop some of these. We're going to develop a theorem where we're going to be able to check this off. So As we mentioned before, not every function has an inverse function. Theorem 5.6 suggests a graphical test for those that do. This is known as the horizontal line test for the inverse function. This test states that a function f has an inverse function if and only if every horizontal line intersects the graph f at most once. So what we're saying is that this function f has an inverse function if if every horizontal line only touches the graph once. So in this example, in this function, it touches the graph twice. It touches the graph twice. So this is suggesting that this does not have an inverse function. What about this one? Well, this one does have an inverse function because notice that the original function is only touching, the horizontal line is only touching the graph only once, right? Only once. So this is known as the horizontal line test. The next theorem formally states why the horizontal line test is valid. A function has an inverse function if and only if it is one-to-one. If f is strictly monotonic on its entire domain, then it is one-to-one, and therefore it has an inverse function. So this theorem allows us to be able to determine whether a function has an inverse without graphing the function. Obviously, if we have the graph, it will be easy for us to determine this using the horizontal line test. But if we don't have the graph, we don't want to graph it, right? It's as we've seen in chapter 3, it takes a lot of time and a lot of effort to be able to graph a function. So we are developing algebraic method to determine whether a function has an inverse, and that is it has to be one-to-one and it has to be monotonic. We're going to define what does it mean to be one-to-one, and we're going to define what is to be monotonic. So first of all, here we can see this graph, right? We can see the graph has an inverse because every horizontal line is only touching the graph once. In the second case, the second graph does not have an inverse because it fails the horizontal line test. Now, we are making those two conclusions, right? So now let's talk about what does it mean to be monotonic and what does it mean to be one-to-one. All right, so the easiest one to think about is monotonic. Monotonic, and we already defined this word before. Strictly monotonic means that it is either strictly increasing or strictly decreasing, right? So in this example, this is strictly increasing, right? It's always going up. There's no one time that is decreasing, right? For example, this one is increasing. Remember that we read it from left to right. This is increasing, so it's still fine, right? It's fine. But then at some point, we change direction. We change from increasing to decreasing. This is no longer monotonic, right? So it's not. So this is not going to be monotonic. Another thing we can talk about this in this example is f is not one-to-one. It does not have an inverse function. So we can say that it is not one-to-one because some of the values are repeating, right? So we'll talk about that one in example B. From the graph given, it shows in the figure on the side, you can see the function does not pass the horizontal line test. In other words, it is not one-to-one. For instance, it is not one-to-one because f has the same value at x equals -1, x equals 0, and x equals 1. So you cannot have the same value in the function, right? Notice that x equals -1, it's going to be 1. At 0, it's going to be 1. At 1, it's going to be 1, right? So this is failing the horizontal line test. It's failing the one-to-one test. And we're gonna show some skills on how to be able to show this. All right, so Let's move on to the guidelines for finding an inverse function. We'll begin with the first one. Use theorem 5.7 to determine whether the function has an inverse function. Number 2, solve for x as a function of y equals g of y. Interchange x and y, the resulting equation of y. Define f of f inverse as the range of f. And verify that the inverse are true. So we're going to do that. So we'll find the inverse of f of x. Now, one thing we know about f of x is that this is monotonically increasing. We can see that it's always monotonically increasing because it's a square root function, right? And we have a simple polynomial inside the function. So this is increasing, and a square root of function is also increasing. So that's sort of satisfy the one-to-one condition. Next, what we're gonna do is we're gonna set up the equation. We're gonna say this is the original equation. We're gonna change this into y, right? Because f of x equals y, and then from here we're gonna interchange x and y. So I'll write a few notes here. Change y for f of x here, right? And then here interchange x and y. And then here solve for y, right? So once you interchange them, you're gonna start solving for y by we're gonna start by undoing we need to solve for y, so we're gonna undo the square root by squaring both sides, and then we're gonna add 3 on both sides, and then we're gonna divide by 2 on both sides. So there you go, we solve for y. Once you have solved for y, then you're gonna this new y is going to be your f inverse. So here, the original one, you started with y equals f of x, but once you did this interchange here, this is no longer y. This is not longer f of x. This is now f inverse. Okay. So we found f inverse, right? And obviously we will check, and that this is true, and I'll leave that for you guys to do. Verify f inverse equals x on your own, and also, oops. Right, so verify that on your own. All right, and then we're gonna define a domain for f inverse, right? We're gonna define a domain for f inverse. And so the domain of f inverse can be easily computed by looking at the original function. So the original function states that, right? You can think about what would be the lowest value if you can figure out the range. What is the range of this? How low? What are the values of y that you can get from here? Well, all we have to do is figure out how low can this function go. Well, the lowest that this can be will be when when this is 0, right? This is 0. This could be 0 whenever you have 1.5, right? 1.5 times 2 will give you 3. 3 minus 3 is 0. So the lowest that this can be is 0. The highest that this can be, well, there's no restriction, right? This can be as high as it can get. So therefore, the range of f of x, the range is 0 to infinity, which becomes the domain of your f inverse. That's sort of the rule of thumb, right? Let me rewrite this again. F inverse is going to be, the domain will be 0 to infinity. Okay. All right, so we're gonna go back now and sort of practice with this example how to test whether a function is one-to-one without obviously looking at a picture, right? I mean, we know that sine of x is a periodic function, so we know it just continues to go forever, right? So we should have at least some sense of a sketch in our mind of this function. Now we're gonna show that this is not one-to-one because there is at least 2 points on the graph where they repeat each other, right? So at x equals 0 and x equals pi, the values are 0. So I sort of did that. F of x is not one-to-one on the entire real line, since f of 0 equals sine of 0, which is 0, and sine of pi equals 0, which means is f of pi. That means that f of 0 equals f of pi, and that means that at these two values, right, they are the same, right? They lie in the same horizontal. They lie in the same horizontal, so therefore it fails the horizontal line test. That means that these two are the same values of y, but their x values are different. The next part of the question is asking us to show that within this interval, the largest that this is the largest interval, center and the origin, on which f is strictly monotonic, right? So we want to show that if we cut off this graph, right, if we cut it off from here to here, that we can argue that this is going to be a strictly monotonic equation, right? We know that overall, in the entire domain of sine, this is not strictly monotonic because this is decreasing, increasing, decreasing, right? So it's not strictly monotonic. By the way, just a quick reference to monotonic. The word mono means one direction, right? So it's only one, right? So once you start increasing, you gotta stay increasing, right? That means that's a strictly monotonic definition. So the way we're gonna show that this is strictly monotonic, that it's always increasing, well, we know that if the function is increasing, that means the derivative has to be positive. So we'll do that, and we're going to show that that's actually true. We'll observe that within these boundaries, the derivative of f is going to be cosine of x. Well, what do we know about cosine of x between those two values? We know that cosine of x is going to be also sort of a periodic function, and I'll draw here the function here like this, right? It goes like that, right? But within negative pi over 2, the function is positive, right? Cosine is positive. Cosine is positive in this part. So within negative pi over 2 and pi over 2, the cosine function is going to be positive. So therefore, the derivative of f is going to be positive. So therefore, f is strictly monotonic for negative pi over 2 to pi over 2. Okay. All right, moving on. Now that we have sort of defined our inverse function, we know how to find an inverse function, we know how to determine whether there is an inverse function. We're going to discuss some special conditions or some special results from the inverse function. So theorem 5.8, the continuity and differentiability of an inverse function. If we let f be of functions whose domain is in the interval I, if f has an inverse function, then for the following statements are going to be true. If f is continuous on its domain, then f inverse must also be continuous on its own domain. If f is increasing on its domain, then f inverse is also increasing on its own domain. If f is decreasing on its own domain, then f inverse is decreasing on its own domain. if f is differentiable on the interval containing c, and f prime of c does not equal 0, then f inverse is also differentiable at f of c. Now, do you guys notice the increasing and decreasing? So notice that if f is increasing, notice that f inverse is also increasing. You guys notice on the previous notes, on the previous examples, f is increasing, the f inverse is also increasing. Here f is increasing, f inverse is increasing, right? So if this is continuous, then this will be continuous. Why? Because it is a mirror image, right? It's the image of that. So I hope that those rules kind of make sense. Now, theorem 5.6 allow us to actually find the derivative of f inverse using some special condition, right? So we're gonna find out how we can find the the inverse of f, the derivative of the f inverse of f, using the derivative of f. Let f be a function that is differentiable on the interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0. Moreover, we actually have a formula for this. What we're saying is that g is the inverse of f, but the derivative of g is going to equal 1 over f derivative of g of x. Notice that this is interesting because we don't need to find the derivative of we can find the derivative of f inverse by just using the original function derivative and the inverse function. So that's kind of neat. Let's see what happens with this results. So in example 5, we are using this to help us sort of have a better understanding of this theorem. We're gonna be given this function this function f, and we're gonna find the value of f inverse of x when x equals 3. So let's observe that. We know that we need to find f inverse of 3. So what we're gonna do first is we're gonna say, hey, observe that f of 2, when you plug it into the original function, it's gonna give you 3, right? So we know that f of 2 equals 3 by, I mean, that's merely a guess, right? But f of 2 equals 3. Well, what about if I do the inverse on both sides? F inverse, right? F inverse. Those will cancel each other out, giving us that 2 is equal to f inverse of 3. And so we are able to figure out what is f inverse of 3. And that's going to be 2. You can also see if we have a picture of this, we can actually do that, right? The next question is, what is the value of f inverse prime of x when x equals 3? Well, we're going to use this formula, right? We're going to say, well, according to the formula, it says the derivative of f inverse at 3 is going to equal to 1 over f prime of inverse of f at 3, right? So we're just doing the same formula here. Now we can sort of work with this because we know that f inverse of 3 is 2. So I'm going to replace this. Right? According to this, is equal to 2. So I'm going to replace that with 2. So now we just got to figure out what's f prime of 2. Well, we did that on above here, right? We took the derivative of f, then we evaluated at f prime of 2, and that gave us 4. So this whole thing is equal to 4. So we get 1 over 4. So there you go. We were able to find it. But it's actually interesting what we are getting here, because if you notice, we know f prime of 2, and then we have this result of f inverse prime of 3 give us the reciprocal of that. So let's see if that's just pure accident or just coincidence. Actually, if we do it, we have g prime of x, which is the inverse of f. This by definition is dy over dx. Well, we can rewrite this as 1 over, and we know that these two are the same. So we know that these two are the same. So, and we know that this is y in our case, right? This is y. And then f prime of y is going to be the derivative of x in respect to y. So what we're saying here is that these two are going to equal each other. These two are going to equal each other. So we're saying that there is a relationship between those two. And in fact, it is, right? So we're saying that the derivative of y will equal to 1 over the reciprocal of that, right? So we're going to show that in the next examples. So let's graph the inverse of functions that have reciprocal slopes. F of x equals x squared for x greater than 0 or equal to 0. We have f inverse of x equals to the square root of x. Show that the slopes of the graph f and f inverse are reciprocal at each other on the following points. So here is your f, right? This is the order pairs of f. These are the order pairs of f prime. So f inverse. Same thing here. This is the order pairs of f. This is the order pairs of f inverse. You guys notice how we are interchanging them. So I'll just say this is for f. This is for f inverse. This is for f. This is for f inverse, right? Okay. So we're gonna need the derivative of f. So derivative of f is 2x. The derivative of f inverse is going to be f inverse is the square root of x. The derivative of the square root of x is 1 over 2 square root of x, right? We done that a few times, right? All you gotta do is change this to a power form and take the derivative. All right, so let's go ahead and do that. Let's find out what is f of 2. F prime of 2. F prime of 2 is going to be 4, right? So at 2, the derivative is 4. Well, what about, since these are corresponding to each other, what about the derivative of f inverse? The derivative of f inverse at 4. Well, what we see here is that this is 1/4. So is that coincidence? No, that's not coincidence. They are actually going to be reciprocal of each other. Now, please note that this was done at x equals 2, and this is done at x equals 4. And remember that that's sort of kind of makes sense because these two are interchangeable, right? When you're dealing with f and f inverse. So they're the only way we can relate them is by using the correct reference of the order pairs, the corresponding order pair. Let's see if that's true for the next one, right? So we have f prime of 3, right? Because we're using this function, f prime of 3. The derivative f prime of 3 is 6. Now, for this one, for f inverse, we're going to do the derivative of this, but at 9. F inverse prime at 9 will be 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1 over 6. So again, these two are reciprocals of each other. Now please note that we're not doing f inverse prime at 3. It has to be at 9, right? At 9. This one is going to be at 3. This is going to be at 9. So please remember those two conditions. All right. So hope you guys find this helpful. Please, the focus of this is be able to know the conditions of whether a function has an inverse. Be able to actually find the derivative and inverse using this new formula that we have. Be able to show that a function is monotonic and one-to-one. Those are the special things. Be able to find the f inverse, which is just a review from college algebra, and we already explained that the concept of interchangeable and inverse order of the order pairs. So again, focus on a few those things when you guys are doing the homework. Please let me know if you have any questions. I'll see you guys next time.